Okay, guys, you can hear me. Just bear with me for a second. I want to make sure I can have a real video this time, not like the problem I just had a minute ago. So a minute ago, it's the fourth video on this. I've got about an hour and a half now. Second one failed on, the last one failed on audio. First two failed on pre-recording. This whole YouTube thing is killing me. I just want to confirm that it's actually working, that I can hear myself. It's telling me to resume. This is weird. I started a new one and it's telling me to resume. I do not want to resume. Let's see if it's me talking just now. This is weird. I started a new one and it's telling me to resume. Okay, I hope this is a new one and not a resumed video. Okay, let's get to it. Let's get to it. Let me start this up in the background here a little bit. See if anybody pops in. Let's get. It's going to wait a second, just a moment for anybody to pop in to get going. I'll give you a teaser. Concrete. Angular stone, round stone. Angular, round. And we'll talk about the randomness as Latitude likes to think of as just random and causing all the weakness. Well, let's just jump right into it. I have a nice sample here. Nice sample. So concrete gets tested to come out to the correct, consistent PSI. Usually within 100 PSI, it comes out to 100 PSI. And this time, hopefully my volume works and my speaker works so I don't mess this up. I have this beautiful sample of angular stone to show and talk about equilibrium. So everything wants to find equilibrium. If I were to throw this up in the air, it's going to find equilibrium by, well, resistance of the air. It's going to come down. It's going to hit the table in this case and might just stop. Well, it might bounce and then wind up on the floor. Ultimately, it will come to a stop. At that point, it has found equilibrium. Now, I don't believe gravity is correct because it's one directional. It's a black hole. It doesn't work. It means it's always pulling, and there's nothing pulling against it. So that would prove one of our favorite guys wrong, wouldn't it, Newton? So, and he's been debunked quite a few times by quite a few people. That gravity thing doesn't work out. Equilibrium works out. Everything's fine in equilibrium. So right now, to hold this in air, equilibrium is me supporting it from falling over with my hand and holding it from falling down with the right hand, and partly with this. So that's the equilibrium to keep it where it is. If I were to remove this hand, I've got to keep the equilibrium holding, increase the clamp force in the right hand. And it's slipping. You see what's happening there? My clamp force slipped. Now it's there, but I had to change it to find equilibrium for this to work. I had to lean it back. And so all forces have a counterforce. Thinking about concrete and paste, if concrete was on top of this member here, we'll use my chin as concrete. You can imagine how much this would rip my chin in half up to my skull because of the shape of this angular stone with all these points. I'm going to surmise for you guys right now that ACI, using angular stone, American Concrete Insanity Incorporated Company, is insane using angular stone. It just does not follow the proper engineering logic. It does not follow proper engineering logic. Proper engineering logic says if you put something with angular in a point like this and put a load on the top, you're going to it's a wedge. You're going to cause an effect where it wants to split it. Well, Angular concrete. Angular concrete. And I did a foam. You know, I love some spray foam to help you guys. She'll do things. Angular concrete is randomly placed here. I didn't go look for anything any certain way. And I used spray foam to represent the concrete and the paste and the mortar. Angular concrete would just be any way. Imagine the force here, down here. So my video states hinging randomness. All right, so there's no such thing as randomness, random cracks. It's well, let's establish that these have been, again, when doing testing, they test, you know, 40,000 pounds of concrete by taking samples out of it, out of a 10-yard truck, roughly 40,000 pounds. And when they test multiple cycles of it, it keeps coming back to about within 100 PSI. So it's not randomly placed as Latitude. I'm having a discussion with Latitude on the other channel there that I have about the randomness is causing the cracks in his opinion. The randomness is the cracks propagate through the randomness. I'm saying no, that there is no such thing as randomness. If you were to throw a coin up into the air, it's already been determined how that coin's going to land, or if you decide the last second to grab it, it still landed. You're still going to turn it over at one point and see heads or tails. It's already, and if you turn it this way, it's heads, and if you turn it that way, you'll be looking at tails if you place it down on the table. It's not random. There's a reason behind everything. There is no random at all. We are not random. You're not created as a boy or a girl by random. It's because, you know, that seed and that little eggy got together, and those two got together to create a male or female. Not random, as they tell you. There is no random. Tell me one thing that's random, and I'll show you the cause of it. If I were to drop this here, it's not random how it lands. It lands because of the weight, the resistance, however the shape of this, the size it lands. It will crumple and crinkle this based on how it impacts. It's not random. Sorry. I had to blow my keyboard. So these are angular stones. Placing the concrete this way, you're loading it down. As you can see, if this is paste and your square inch loading is here, you can see how this is wedges, hinges, right? This creates a load down that wants to push these two apart. What happens to the next section? It wants to compress this part, which wants to compress this, which might want to compress this, but want to create a, right there, since it's angular, create tension under here and compression down here, tension on the face of this, compression down here. You see what's going on there? If this is pushing down, it's creating compression in that path. If it's creating compression in that path, this one is experiencing tension because it's not part of the load path. This one's trying to go down. This one is trying to stay where it is, creating a hinging. Now, if the soil could compress on this side, it would, and then you'd see a crack, and it represents itself as above. This represents pea stone. And you guys know that if you're creating an arch, the Roman archways and the viaducts and all that, they're what? We just said it. They're arches. They're round in shape. They're an arch, right? And it's proportional. It's an arch because arches are great. They transfer the loads out beautifully. What doesn't transfer the load out beautifully? Mostly these damn things. They create a triangle, or triangle we know to be put in bridges, creating a compression and tension moment, right? Here's your built-in the triangles you're making. If I were to spray foam around this and then remove this, you would see a truss system that's designed to boot compression and tension. But you have in that system a center design section, a angular stone that wants to, when you load it at the top, wants to actually split it apart. Wants to split it apart. This is how you would make a jackhammer is made this way. They have a point on it, and then they jackhammer the concrete. This is your jackhammer. Angular stones are. Angular stones are just the most stupid thing ever in concrete. There's an angular point. Loading here, this angular point's pushing back, creating a weak point from here to here. Into concrete. This, whatever force you're applying here is being countered by a triangle, a pointing section here. As that's loading down, let's say it's going 45. It now wants to come to here, pushing this to that side, creating what? If it's pushing that, it's creating tension here. So concrete, this is just so chaos. You know, it does come up with a norm, because they use the same size stone, say 3/4 inch pretty much in a mix, 3/4 to 1 inch, and say a mix that like this would be 3/4 to 1 inch mix. You will test it with the paste you used, the sand, and let's just use that. No other additives, and the stone. This creates a PSI that would be consistent of whatever you added your paste and sand are, which is going to be maybe 4,000, let's call it. They compress it, they test it, crush. They test multiple versions of this guy, and they keep coming, well, this is 4,000 PSI with that mix. Awesome. That's it. But then we say, okay, now we have a load weighing 2,000 pounds, so we say it can take 4,000 pounds. Is 4,000 pound concrete, we're covered. We got 2,000 PSI concrete here. The vehicle is actually only putting on, when you do the tire, the base of the tire and all, it's only loading down maybe 800 pounds per square inch. So theoretically, there's no way a car hypothetically putting down 800 pounds per square inch on the tire tread, which is way too high. I just made that number up. Let's call it 100 PSI per square inch on the tire. Each car is going to be different. Let's say 100 pounds per square inch. How the hell on earth does a 100 pound PSI surface area create a 4,000 PSI concrete? How does it break it? It would be not possible, except for, and it can't change. The vehicle can't change all of a sudden and add all its forces into 1 inch. So it's over the tire base, tire base. So it's going to distribute that load all the time. So how is that possible that, unless you lower the air, right? And if you increase the air, then you'll get a little more, but a little bit more. So how is it possible that it has to be able to create a 4,000 PSI to break it? Well, because we know concrete breaks in about 10% in tension. So let's say let's change the numbers again. Let's say this is 4,000 PSI concrete. And that means you only need theoretical 400 PSI to cause failure. Your car's putting 800. So you're like, well, no, that couldn't be it, because it would have broken the first day. So that's not it then. Well, what is it? So the car is not giving greater than 400 PSI. It's still at 100 PSI. So how did it break it? Because we need 400 to break this in tension. Well, I'm going to show a free body diagram using, well, I like showing real world stuff like sand. And so imagine sand, right? The pile of sand that I show in my other videos. If I were a vehicle and I were coming along with the front tire and I were to stop, well, engineers like to think of that's the dead load. All right, the vehicle weighs this much, the dead load's on this, it's not going to break it. Here's the problem, though. The vehicle is not just stopping. It's stopping and surging. It's surging. That surge is concentrated in two tires, the two-tired vehicle in the front. I'm not counting the back tires on the concrete at all. So it stops. It stops. Look at this stone. It wants to go forward, or it does not want to go forward. So it hits it. We calculate 3,000 PSI doing testing also vertically, not horizontally. Look what I just showed you. It looks like that, the free body diagram. It's a surge. It's a surge. When it does that, it wants to pull. It wants to pull. Scratch my head. Got fleas. As the car stops, it would stop just like that. But say today he stopped at 15 miles an hour. It created a little more pulling. Look at my right hand not moving. And it stopped. Next day it goes 30 miles an hour, run into the house, and it stopped. It pulled. When it pulled like that, the concrete experienced a charge laterally also. All it needs is 400 PSI laterally also, because now it's being charged sideways, laterally. Laterally is where you're seeing it. So sometimes when I look at cracks in the driveway, first I try to think of is the base. Is it being washed out? Has it gone through a bunch of cycles where the soil would have consolidated through water, expanding and then contracting and creating a void? Now I'm able to see an easy I have room now for the concrete to move, to compress. Here it is on the soil. I have no room for it to move. When it consolidates, it creates a little bit of a gap. Now I've got room for it to move down and crack, right? So I could split this if this could maintain and I had the ability, I would break it like a karate chop, right? But if I put it on something firm, I go to break this, it might experience its own tension and failure, but it's going to transfer the loads down to what's below it, as long as they're snug and tight. So I look for that. One of the ways I can indicate that if that's happening is I'll look at the two surfaces where the cracks are. And if one is higher than the other, well then yeah, the soil's eroded below. It's simple. And the other one lowered itself. Maybe not compaction. Maybe the water did cycle. Maybe there's a drain running across there somehow. It's something as simple as that. You can find it. It was discovered by the car driving over it, experienced more than 400 PSI while I was braking as it drives over many, many cycles of pulling in the driveway and pulling out as you slowly pump your brakes. And then a crack appears. It just needs 400 PSI over that plane, because the crack is initiating. So now, but sometimes I see cracks that are like cracked, and they're like perfect, man. They're like, what? They're like lined up. They're not high or low. How do you get a crack in the concrete? And people say, well, they're expansion cracks. Expansion cracks. That's their answer, expansion cracks. Well, fuck me. I've heated up some concrete pretty damn hot, well above the temperature, and I don't get this damn concrete. I get a spalding in my face, though. If you put a acetylene torch on concrete, it will pop in your face. If you heat it evenly, nothing happens. You can look at all the different hot locations. You're not getting these expansion cracks. So this expansion crack, that's an expansion crack. What's taking place is that loading is happening. It's creating a lateral shear. A lateral force is creating the shear in the concrete because it's in tension now. And it breaks, and there's your crack. And your path is divided between the two tires, doing it at the same time, parallel from each other, creating its own little two points of contact, like that on the concrete, a surging, if you will. That, whatever's behind it, is where the forces are experienced, and the crack can develop right behind this. It's usually not going to develop right on the tire tracks, because it's going to be translated too much in the compression, experience the least amount of tension happening, the least amount of separation. And I see that with concrete cracks that are like right on top of each other that have no up or down. And so that's what I see there. Other engineers would call that expansion just because they can. And you're like, well, what temperature caused that expansion? I have found no testing to show expansion cracks. It's just something that's theoretically made up, that concrete expands when heat hits it, and those cracks, therefore, must be somewhere where the concrete decided that it was not going to expand and everything around it was going to expand. Ironically, in a straight crack. Really? That's your best answer? You guys are on crack to believe that. Angular stone is crap. ACI, American Concrete of Insanity Incorporated, is telling everybody that put this in here, you'll get great compressor strength over the round stone. Well, you've got cracks you're dealing with because of all those tension moments that's created in here. As that car, it's the paste on top, stops. It's creating that hammering going on here, which creates let's see, if I could push this, and this is bonded pretty good with this paste, with this foam. If I could push this, I'll be pushing this here, creating a hinge effect, pushing this one backwards, which means I'm actually creating a tension opening here. This is pushing down, created a ass end hinge here, pushing against this one outwards, and now we can get a crack up here. I can produce this by using a plaster, a soft plaster, and I can push this and create that same crack, a compressive moment here, in fact, that this stone is, say, 14,000 PSI stone. We already know that the concrete is 4,000, the paste that they made is maybe 4,000 PSI. These two are not compatible. 4,000, 14,000. You've got a soft material hitting a harder material. This material fails. Until you get into the high strength concretes, you'll always find cracks, always deviating around stone. You will never find, I have never found, a crack that went through stone, when a crack has appeared. It always takes the paste. Takes the paste. So it will take the paste because it doesn't have it takes these two, this one, just as it's breaking, there's no forces that are greater than 14,000 psi that's going to come down here. That will not decide to also first go down to 4,000 psi, and that's that least resistance, right? We know about least resistance. I'm not arguing that. That's equilibrium taking place. So there's your angular stone. Here's your round stone. The round stone, doesn't the round stone come more closely to this? There's no angular, there's no pushing back. There's no pushing back like this. This makes it clear. This is round. Here's round. Oh, that's much better. I'm not even afraid to do that. This one I'm going to cut my damn chin open. Again, we know that arches, we know from the Romans and everything else built, arches are the strongest. What's closer to an arch? Pea gravel or this angular stone? ACI is BSing because it must be a lot of marketing for angular stone over having to resource this. Now, let's talk about one more thing on this, tension failure and clean stone. I showed in the other video on my other channel how your angle of incidence, your repose is much less when you've got dust on your angular stone. I show it in the other, you got to go to my other channel on the repose. When your stone is washed, it's going to have more slip to it, more slip than if it has dust on it. In this case, we have our bonding product, which is the paste. So you have your clean stone because we don't want a bond breaker of dirty stone. But ultimately, stone makes dust when even if you wash stone and you start throwing the mixes together, you're grinding stones together. You're going to get some stone dust in there, which is going to create some issues. This is going to be more flow, less friction when you throw a bunch of these together. You're going to come away with less dust than you would with this. So this is your bonding effect. This will bond tighter to this surface, with the exception of what I just said. It's a smooth stone. The angular stone has porous material in it, which gives you more bite, right? Theoretically more bite, but it also gives you the deflections, the pushing back. Remember, you have an equal reaction, and it's unpredictable. It's not as predictable as round. Now I've looked at tons. I guess I'll pollute the water a little bit. You guys can look at the first time that somebody really believed, like I believed, I think. They went into the, is it the Washington, that damn spear in Washington State. I always forget the name of it. That was the high strength concrete they used using pea gravel. And that seems to got pushed under the rug. Nobody seems to be paying attention to that. That's your example of a life cycle that we see now. It's in the air. We suffers the wind, the deflection, everything else, and yet it's not being monitored like it should be for the advantages of T-stone over ridiculous angular stone. I said I would do a comment for some guy. Let's see if any comments first. A comment for video's not loading. Hold on. Okay. So cool. Give me a second. I'm looking at the video. I guess I won't do it. Equilibrium, random, hinge. Explains all in life. So everything, that's the title of the video. So everything has equilibrium. I had a little itch on my nose. I just had to scratch it, put myself back in equilibrium, right? I'll rub it. So this by itself, before you load it, it's an equilibrium. No cracks are present. It's just going to be perfect. Now, as forces applied, as forces happen on it, such as drying out, rain, cycles, things like that, that's another force. And if a crack develops, that's because equilibrium was reestablished. The cracks are establishing equilibrium. They're not something negative. It's something establishing equilibrium in the design. They're signifying something is wrong, such as the FIU bridge collapse. They were not a mistake. They're signifying something is wrong in this design because equilibrium has to be established by showing a crack at this point. Now this we know that it's going to obviously be pretty damn flexible for some time to come because it's on paper. Now to remove the paper, the backing, which acted like a truss because it was bonding the surfaces together, and look at a free body diagram of how that actually would look. There's your free body diagram. I wonder what that looked like. How the truss plate looked like. It looked like that. That's what this truss plate looked like with some gaps. So if it took a flexural moment, it had a gap here. I don't know what that gap was. A stone. We could put it back together, and you can do crazy stuff analyzing things. And there we have it. So this is what it would look like on a concrete placement, if you will. And you can see, for example, here, the forces coming down. We only have to defeat to get this paste. A load here could defeat it and create a hinge. Because if this went down at all, it's a hinge now. It's going to push this up, hinge here. Push this over. You see the dynamics of it? Pushes this over. It's all creating wildness. That's on that side. On this face, same stone, same thing, but now there's paste here. So now it's got a shelf though. It's going to push up. This is going to push in at multiple locations. That's my point about angular stone, is that it has to take the force and push back the same way. Let's go ahead and look at this little free body diagram. If I trigger you guys on free body diagram, so be it. So be it. You do your explanations. That's what it would look like. That's what it would look like. That's what it would look like on the back side. What's holding together. That's the side we looked at. Now this is kind of cool. It's kind of cool because what I can do here is I can hold it here. And we can apply a load right here, let's call it. And we can watch this thing react. Since I put foam in it, we can see how it transfers. And you can watch the reactions. This is foam. Yes, it's foam. All right? Get up. Get over yourselves. Grow up. But you can see how it's reacting. That a hinge is creating. This back end is rising as this load takes this. It's happening whether you like to believe it or not, clowns. So here would be an overhang, and this would be the holding point. And you could see where it would do that. Hinging here, but that's a pinpoint, pushing back here. This is helping you see free body diagrams. Pushing down here creates what? Tension across this. If I could hold this here and push down on here, we would see the stone here do a flexural moment. Now I'll take it to a failure perhaps. Let me see for you guys. You see here it's crushing inwards as this loads here. And we have a round stone though, of course, that's going to want to deflect all the forces kind of beautifully and wrap around, theoretically wrap around like this. So hold it this way. Let's push down this one. It's already ripping apart. It's already losing tension. And what did I just show you? It's losing tension. Why? Because it had more surface area. The angular stone that I mentioned had a better bite for the profile was better to bite, for the paste to bite onto. And now you see where it goes full circle against the formula in tension. Because of that bite, it was able, you applied forces here, it grabbed, the forces were so concentrated and able to hold the paste, if you will, hold onto this piece and not this one, we get a break. Up here, you would look at a tension break. You would see a tension break. And look what happened. All we did was compression down here. And we didn't even get a deflection in this. Of course, I'm using foam, but you're able to see how the reactions are taking place. Car coming across. You got this individual thing. Am I terminating the video? I think so. You guys control that all you want, or you can go to hell. You get to take a choice on that. You get a choice. I'm going to stop the video. Anybody commenting or saying hi or bye? I'm saying bye. Excuse me for choking. I feel like I wanted to add something to this for this other guy that trolled me on my other channel. I think it would take away from this content since it stayed with concrete. So I'm going to leave it at concrete, and I'll just have to get back to that guy another way. So, bye. Thank you.